Thank you very much, Lauren, and good day to everyone. We'll be looking at the materials engineering considerations here of transporting CO2 and a bit on the background industry profile. Cynthia has covered that already. Then I want to look at it from an engineering design perspective, the five top risks in building thousands of miles of CO2 pipelines, some of the environmental and business implications, and then the next steps, conclusion, action plan. The U.S. Hazardous Liquid Network, right now there's about 3.3 million miles of onshore pipeline, and its transport, as many of you know, natural gas, crude oil, and other hazardous liquids. If we further market segment the products being transported, we have about 5,150 miles of hazardous liquid transmission pipelines of CO2. Just a real quick overview of the current pipeline steel grades. Typically, you'll hear of X52 line pipe, X56, going all the way up to X70, which is essentially the yield strength of these pipes. These pipes can be, in some cases, up to 7/8 to 1 inch in thickness. Now, the conventional carbon steel that is currently used for natural gas and oil is really being considered for CO2 pipelines. And that raises a concern. And the second point is it's anticipated that the same materials approach is being considered for the CCUS pipelines. And in some cases, we need to look at the internal corrosion resistance and the hydrogen embrittlement risk of the steels that are currently being considered for CCUS. The three areas from a materials engineering perspective that we want to look at, which is in some cases similar to natural gas, but in other cases a bit different: corrosion, hydrogen embrittlement, and the weld heat affected zone. The weld heat affected zone, essentially where we join these pipes out in the field, bringing the CO2 to the carbon capture facility. The properties that are of concern is in vintage pipelines. And by vintage, we're talking years of service, but also in recently constructed pipelines, we have this concern about corrosion. The map I showed earlier of all the pipelines, the corrosion cost is estimated at $7 billion annually for onshore and liquid transmission. Again, this is maintenance of a huge infrastructure. And the $7 billion in some cases encompasses replacing pipelines that may be of age. They may detect cracks, and in some cases have to do field repairs. In the current root cause analysis of pipeline failures that have been done over the years, and a lot of this work has been done in the area of methane, many in the engineering community are looking at upgrading both the steel pipe material / welding procedures and how we join. And the second big area are the construction practices in the field to make sure that we've got the best practices in terms of constructing these pipelines. I'll get into the 5 concerns and risks, again, from an engineering perspective. The corrosion risk is internal with the media that's being transported, the CO2, and its chemical composition. The external corrosion which where the exterior of the pipe is in contact with soil. And, Dominic will be addressing some of that. We see in the field, in areas where there are pipe and culvert materials, corrosion issues really starting to evolve in various areas of the country. And with CO2, we form what's called carbonic acid, but because we are catching waste gas, CO2, there could be nitric, sulfuric, and hydrogen sulfide. Let's quickly look at the mechanism here. Is that the concern is this is not pure CO2. And a lot of the natural CO2 that's used for enhanced oil recovery is quite clean, and hence less of a threat to the corrosion and hydrogen embrittlement of the X52 to X70s. These gases are being captured off, say, a power plant. So you will have some hydrogen sulfide, some NOx and SOx impurities. And the other variable we have here is the moisture content plays a big role in the corrosion of the steel. Essentially, when CO2 is wet, it creates carbonic acid, which corrodes carbon steel. So moisture and the variations in the temperature and the pressure in the pipeline operation can create certain conditions when the chemical reaction of corrosive attack of carbon steel could happen in the pipeline because of this mixture potentially of the impurities and the carbonic acid. Now let's look at it from the engineering operational perspective of operating pipelines 24/7, 365 days a year, and also the carbon capture plant where we're doing the processing. Again, the actual chemistry and the residual content of CO2 streams being processed is an unknown and really needs to be shared with the design engineers. More information would really be needed then if we had these chemistries. We'd actually be able to do corrosion testing of different steel materials of the blended CO2 flue gas that's being transported to the CCS facility. Of paramount importance in many operations is the control of the moisture level. And in this case, the control of the moisture level in the CO2 will affect the behavior, the corrosion behavior. The operational pressure and temperature control, of course, is very important as we're transporting the CO2 many miles to the CCS plant. Number 3 risk is a business case example from a couple of years ago, the Petronova plant. And this was at the time a funded government project of a CCUS facility that was connected to a coal-fired power station in Texas. And it closed, shut down early. And the reason it was shut down, as reported, of course, the CCUS was for enhanced oil recovery in Texas. It turned out that the break-even flipped on operating this plant when oil went to $75 per barrel. So, in any manufacturing operation, right, we need to know our break-even and have different alternative plans in case the price takes us below the break-even. Why did it shut down early? Well, because of the oil price. Well, as I reviewed the public report through December of 2019, about 3 years of operation, there was a 16% shortfall in the total amount of CO2 captured. Yet the project really demonstrated the success of capturing CO2 off a coal-fired power plant. So the process or the chemical engineering side of it worked out. However, there were reported operational issues, very qualitative, not quantitative in the report. But there were operational issues with leaky heat exchangers, calcium deposits in the system, unscheduled downtimes. And it would really be interesting to get a richer understanding of how they had affected the operational efficiency. Some of the story behind why the plant didn't reach its goal of 95% carbon capture. The number 4 concern is there's a number of unproven technological, financial, and environmental risk. And I just like to walk through those with ideas for the next steps. Research over the years has documented the necessity for special consideration when we have impurities in the CO2 feed. It's almost like the laws of physics. There's certain chemistries where certain materials will corrode. And we really need to know the actual chemistry of what we're pumping down these pipelines. In the technical field, we call that a knowledge gap. And talking with modelers of the outflow of CO2, the subsequent dispersion of CO2 following the accidental rupture of pressurized CO2, we need to further identify and do root cause analysis and drill down into the Satartia, Mississippi event where there was a failure. CO2 corrosion data, again, in the literature, it shows a need for additional corrosion testing to get a better understanding of the corrosion rate per year of CO2 in the sequestration or the CCS process. We now move to number 5. So where do we go from here? Kind of outlining the challenges, the engineering challenges, and the materials and corrosion engineering gap for CO2. We'd like to see a definition of the impurity limits for every plant that is feeding CO2 from their stack to the pipeline. The second point of concern is that there has been corrosion study, right? Corrosion engineering for the last 50 years without consistent cost-effective solutions for carbonic acid with carbon steel and even 13% chromium alloys. This begins to take us into the stainless steel arena of materials. The third action is need to look at possible pipeline materials based on the corrosion experiments, and then do a study of the cost, because from what we've learned to date, we'll be looking at higher alloyed materials, which will increase the cost of the pipeline. The clad pipe may be an option, and clad pipe has been used in pressure vessels, in many chemical refining plants. And what that is you still have a carbon steel base material, but you have a corrosion resistant layer of an alloy, which is bonded to both the interior and in some cases the exterior of the pipe. Could be a potential solution. From whenever we're designing, we need to take materials cost into account. And this particular slide is just to give you a feel for current carbon steel X70 pipe is about $2,000 to $2,500 per ton. And let's call that a cost multiplier of 1. If we go to the stainless 304L or the stainless 316L, where we're getting chrome in the steel, we can increase the cost anywhere 3 to 5 times on the 304L. But you know, if we clad that steel, a carbon steel pipe, instead of using stainless, now we're up to 4 to 7 times. Now we move down to other possible alloy materials, and you get into the Inconels, the nickels, and some of those begin to get you into the super alloy arena, which is very expensive materials, and you can see the cost multiplier is double digit. The point I like to make here is that when a materials designer does not have enough information about the media being transported through a pipe, you need to design, in some cases, over design, because you're uncertain of the corrosion that you'll be experiencing in a 24/7 day operation. Number 1 and 2, a cladded pipe, interestingly, is applied in offshore sour gas areas, saltwater regions. Why? Because of corrosion. Because of corrosion, we have clad pipe in offshore. Number 2, the materials engineering outlining the ideal grade for the safe transport of CO2 media is complicated. And it really depends upon the chemistry of the transport media and the processing conditions during transport, which again, in the operation, what's the temperature, what's the pressure, how much variation are we getting in the transport? Just touching quickly upon the Inflation Reduction Act and the financial implications. Certainly, Sandia showed how there's this metric of carbon capture and credits, and moving, 50 to 85 up to 180 for direct air capture. One of the points I like to make is that the higher this credit is, it's going to open the door to other industries wanting to hook up their industrial stacks to the pipeline to facilitate receiving some of this $85 per ton. So there's quite an interest, not only in the oil and gas industry on this, but the steel mills and cement plants might find some of this to become viable, especially with the kilns in the cement industry and the furnaces in the steel industry. The cost of operating a CCS is a huge unknown. Petronova example. Satartia, Mississippi, failure analysis and understanding how we prevent this from ever happening again. We can learn a lot from the Satartia, Mississippi failure, and then include that knowledge in the cost risk analysis when companies start building these plants and they're looking for a positive return on investment, as well as cleaning the environment. I'd just like to talk briefly about Solyndra. And I'll mention Solyndra here because this was another taxpayer-funded initiative about 10 years ago to address climate change needs that became costly because of technological and economic problems that arose. And what happened, the plant only operated a couple of years and there was a loss of $500 million loan guarantee from the government. The company eventually went bankrupt. CCS now, although a different process, etc., the point is here from a business perspective, CCS could be much more costly if a similar scenario is not addressed up front, which we are pointing out here. These unknowns that I'm bringing up. Just because the government is providing monetary incentives, the $8 billion for hydrogen hub and then the CO2 starting to become part of the hydrogen hub, those monetary incentives does not mean that there might not be better technology and scalability for alternative projects that would result in producing less carbon from the onset or capturing it at the source. So in summarizing here, the takeaways I've highlighted. We have a high risk of steel corrosion And from a design engineering perspective, we need more information. It is difficult, if not impossible, to specify steel grades for impure CO2 that we can guarantee safety used over time. CCUS is not a well-proven operational / maintenance technology. And it's proven to capture CO2. However, how are we going to operate a plant like Petronova and be profitable doing it and still achieve our goals? The variation in the chemistry of the CO2 streams that will be coming out of the different power plants, the different industrial facilities that want to pump their waste CO2 into the pipeline, they really need to share the composition of that gas stream. We have a major risk to pipelines and the surrounding ecosystem, of course, internal as well as external, in case we get a leak or a crack. And then from a global perspective, the CCUS solution is more a longer term solution. And, you know, with my international actions and colleagues in Europe, although they're working on CCUS, there seems to be a shift toward more of the European green hydrogen approach is the root cause solution. I advocate for laboratory corrosion testing of alternative materials to start to quantify how we will corrode, at what rate per year will we corrode the carbon steel pipe, the alloy pipe, the clad pipe, etc. There's a lot of funding, right? The $8 billion for CC and for hydrogen. I advocate a material science and engineering research program funded by the government and private industry to really study these corrosion issues and develop materials before the pipelines are constructed. Finally, there's unknowns that I've addressed here: financial, environmental, and technological. And from my experience in the steel industry, with the liability that would be involved as a supplier of CCS pipelines, I would want answers to the critical questions I have presented here today before supplying a material for CCS applications. And I certainly would not approve the repurposing of any existing steel pipeline to carry an unknown mixture of gases from a liability standpoint. So I believe many of my colleagues in the steel industry are equally concerned. And with that, I thank you for your time and open up for questions and turn it back to Lauren.
Thanks, Steve. That was a really interesting presentation, and you really generated a lot of questions in the Q&A. Really quickly, though, I will highlight one of our participants, Matt Smith, has had his hand raised for a bit. And Matt, I'm sorry we didn't get to you it's a little bit more promptly, but if you're still there and you have a question, please do feel free to pop that in the Q&A, or I can call on you and you can speak. Matt, you're unmuted. Matt Smith.
Oh, sorry about that. I think my hand was raised unintentionally. I think I accidentally pushed that button. But thanks for this excellent presentation. It's been really informative.
Thank you.
So I think we'll go then to the questions that are still open in the Q&A. Matt Rhoda, would you like to speak for yourself, or do you like, I can go ahead and read your question. Matt Rhoda asks, I saw a recent draft report that stated there may be triple 48-inch CO2 pipelines going up the East Coast and in the Gulf South. Is this size and amount precedented? How does this massive size and putting multiple pipelines next to each other increase risk?
Yeah, and thank you, Matt. That's an excellent question. The doubling of pipelines happened a few years ago, and now we're up to tripling. And certainly it further increases the risk. It begins to get a bit into concerns regarding subsidence. This close proximity, if you have a failure, let's say we have pipe A, B, C, and we have a failure in pipe B, how does that release of gas affect the adjacent pipes, especially if we're releasing carbonic acid? So herein comes, if the industry wants to lay multiple pipes, it further answers one of the questions about, we need an alloy material on the exterior of the pipe as well, the cladding, to prevent exterior corrosion. The second side, I'll put on the business hat. Certainly high volume. When you have 3 pipelines in a row, you take a look at those gallons per hour. So I think when you would run the economic analysis at the company, you're really increasing your productivity.
Thanks, Stephen. Another question is, are there any completed CCS projects with public data on how they're performing?
The only one I saw was the Petra Nova, which was a DOE project, but I have not seen anything. And why the reluctance to share is a concern of mine.
Okay, another question about Petra Nova. Does the Petra Nova 16% miss include the CO2 from the gas-fired power station that had to be built to provide electricity to run the capture equipment?
I believe it did. I'd have to go back to that report. There was a big focus on just capturing the CO2, but we'd have to go back, and it's a public report, so you might be able to find some of that information in the report. Thank you. Here's another question. Which of the concerns, such as corrosion, also apply to air capture of CO2? It would depend on the moisture at that given facility and the NOx and the SOx and the hydrogen sulfide. That being said, we're not having to transport it thousands of miles. And you could self-contain your direct air capture system. So when we would look at the material cost, it might be more feasible to do capture right at the site with these alloy materials. And it offers the possibility of being able to operate safely. Thank you. But we could go all day. We have several questions here, but why don't I pick a few more before we take a short 5-minute break? Kathy Martin asks, in addition to sharing CO2 gas impurities, does an agency like PHMSA create CO2 purity conditions, such as limiting moisture or acid forming impurities with numerical standards in order to enter the market pipeline? Not yet, to my knowledge. It's still quite general. Yeah, and hence it kind of dovetails the obstacle we've run across from a materials perspective of having clients share information with us on the purity or impurity. And then once that data is obtained, I think it could open the door for PHMSA to perhaps begin looking at that. but you need numbers, right? We need data. So that's one of those unknowns. Great question, because that's where we need PHMSA to be congruent with the changing conditions.
Okay. I have one question from June Sakara. We'll get you unmuted. While you unmute yourself, I'll ask Stephen one question about how is the corrosion of pipelines affected in underground? How is corrosion of the pipelines affected in underground areas where H2S and salt water have been disposed?
I assume he's talking the external corrosion. And here you have this double risk, right, of the hazardous impure CO2. And then you have the external corrosion. So the steel is being infiltrated, if you will, from both sides. And of course, H2S with water makes sulfuric acid. And sulfuric, we know about the corrosion rates of sulfuric acid in steel, and there's ways to control it. But it's a bit of a double edge. You know, we're getting attacked from both sides.
Thank you. June, do you want to go ahead and ask your question? I see you're off mute.
Can you hear me?
I can, thank you.
Okay. So thank you for this presentation. I've been doing research on carbon capture and storage for 3 or 4 years now in a focused way and have a couple of published papers on the topic. And I approach it from a public policy perspective, a public need perspective, what makes sense for people, what makes sense for citizens, what makes sense for how our tax money is being used. And so I'm wondering, I mean, the presentation that you gave is from a business perspective. It's sort of like, you know, how pipelines, you know, avoiding extra costs and things that could be done to make the pipelines safer, that is, you know, not repurposing pipelines, et cetera. But in fact, every bit of carbon capture and storage that's going on right now in this country, in the United States, I won't speak for the Norwegian situation, is being enabled exclusively. It's happening exclusively only because of public subsidy taxpayers, mainly 45Q, but now mainly 45Q tax credit, but now with tremendous subsidies, as we heard earlier. So in my research, I and my colleagues came to the conclusion that there's no form of CCS that ought to be paid for by the public, since basically what's going on is that these are polluters who are putting you know, catastrophic amounts of CO2 into the atmosphere with the results that we know. So that if any CCS is going to be done, it should be done exclusively at the expense of the polluter, whether it's a power plant or a steel plant or a cement plant. So I guess what I want to ask is, would you sort of say what you think about carbon capture and storage, including pipelines and the storage, from the perspective of public policy, and does it make sense for taxpayers to be financing this?
The short answer are the companies should be financing this. The companies, the risk, you know, without the government support, June, and I've seen some of your papers and they're awesome. Without the government support and the taxes and the queues and all, I like to see what the approach would be with the oil and gas industry. And that's why I mentioned Europe. It's a total different landscape in Europe, and how they're progressing with green steel making, and eliminating the source of carbon, and making steel with hydrogen. So the accountability ought to be with the company. It ought to be with the company. And we have such unknowns, and that's why I brought up the Cylindra just as a business case example. But some of the indicators are, if there wasn't that government loan, like these loans and subsidies that are happening today, what would be the direction of the fossil fuel industry? Are they really?
So you do feel that all of the subsidies for at least we're not talking about DAC, direct air capture here. That's a whole
Correct.
other approach. But you basically are essentially agreeing with me that there should be no public subsidies for carbon capture and storage, point source capture, and the pipelines and the storage. No subsidies whatsoever.
Exactly.
Okay, that's good to hear.
Exactly.
Thank you so much for great question.
Thank you, June.
I think we have time for one or maybe two more. One question is, does the moisture in wet CO2 primarily come from ambient humidity? And is it fair to say that CO2 corrosion is a bigger concern in humid versus arid environments?
To the second point, the environment, your geographic location is part of it. However, depending on the moisture level of the coal in the coal-fired plant and the raw materials in the process have some inherent moisture. Sometimes you have moisture from the materials that are combusting. So it's both material moisture and ambient in your climate.
Okay, and then maybe one final question about the existing CO2 pipeline network. Are they currently at capacity?
Barely. Last time I saw, they are close, and most of it is for enhanced oil recovery. And again, most of that is the naturally occurring CO2. It's a different chemistry, and that certainly would be part of the corrosion experiments, to make comparisons of the existing CO2 pipelines have a track record, but we're talking a different material media with CCS.